Hello everyone, my name is Zekun Shen. Today I'm glad to be here to present our paper, Drifuzz, Harvesting Bugs in Device Drivers from Golden Seeds. It's a joint work with my NYU colleagues, Ritik, Roongta, and Brandon Dolan-Gavitt. So device drivers, as part of the operating system, have two attack vectors. Attacker with user space access can exploit device driver bugs to gain higher privilege. On the other side, hardware peripherals are connected to the host machine via physical ports, such as USB and PCI. And in this work, we focus on the second boundary. Traditionally, developers have trust input from peripherals. However, these peripherals can in fact be flaky. Prior research has shown that device drivers are more buggy than the rest of the kernel. And in our threat model, a bad peripheral can be physically plugged in via ports such as USB and Thunderport. And a good peripheral can also be remotely exploited because they are highly complex and run their own firmware. It's possible for attack like Broadpwn to take place, where attacker can first compromise the Wi-Fi SoC and then exploit the driver bugs to take over the rest of the system. However, it's challenging to test device drivers because there are lots of different hardware and many different drivers. In Linux, there are more than 14 million lines of code in drivers, and more than 4,000 drivers are pre-installed in Ubuntu. And a malicious peripheral can pretend to be any of them to exploit a bug in a target driver. So it's impractical for us to test with real hardware in the loop. For this reason, we chose emulation-based approach to test drivers without hardware. We create dummy emulated peripherals and then feed input to the device drivers through port I/O, memory mapped I/O, and direct memory access. However, a limitation we see is that random initial seeds are usually not good enough. For this reason, we want to learn the good initial seed, but without hardware tracing. Symbolic execution is a testing technique that makes input symbolic and tracks the derived values as symbolic expression. At a symbolic branch, it forks the execution and explores both the true and false conditions. And the collection of path constraints can be sent to a constraint solver like Z3 to check for satisfiability and generate concrete values. However, symbolic execution have hard to test code patterns. It has been previously used to test device drivers by SymDrive. However, complex drivers may contain patterns that make the life hard for symbolic execution. Repetitive checks with symbolic branches can cause path explosion. For this reason, SymDrive aggressively prune the fork states, which can leave parts of the code untested. Concolic execution, on the other hand, explores one path from a concrete input and collects the path constraint. It uses the constraint solver to flip individual branches one at a time to discover the neighboring path. Another popular technique for software testing in recent years is fuzzing. It's popularized by mutational fuzzer like AFL. And AFL starts with some random initial seeds, which we call corpus. Then it runs in a loop to apply random mutations, execute each input, and collect coverage feedback. It adds the input back to the corpus if it discovered new coverage. However, fuzzing has hard to test code patterns. In this example, it can have very hard time to guess the magic values in this example from a PCI driver where there are 2 magic value check of 4 bytes. So we devised the golden seed generation algorithm based on our observations that random seeds are usually stuck during the driver initialization phase. There are usually blocking branches such as status check, version check, or magic value checks. If unmet, the driver would regard the hardware as dead or unsupported and just terminate. These checks usually have preferred conditions that's either always true or always false. We see coverage can increase when these branches become unblocked. So our approach uses concolic execution to greatly increase the number of symbolic branches covered and learn the preferred conditions for each blocking branches. To help with repetitive blocking branches, we use force execution to gather many constraints at once. Recall from the problem example from before, there's a repetitive symbolic branch at line 6. We want to test the always true or always false preference, which one will result better coverage. For normal concolic execution, it can only revert 1 branch at a time, and it would take more than 200 iterations to test the preferred conditions. We can instead use force execution to force the branch on line 6 to always return true or false, and then collect all the past constraints with 2 iterations. And now we can compute the coverage, compare the coverage, and learn that the always false condition will result better coverage. And here's our pseudocode for golden seed generation algorithm. We start with an empty preference mapping, and we run concolic execution on the initial input. We regard all the concolic branches as newly discovered inputs. Then we enter a loop where for each of the newly discovered branches, we test the always true or always false preference. If concolic force execution succeed and discover new branches, we record the result. In the end of the iteration, we select the best preference based on the number of symbolic branches. And then we update the preferences mapping and other local variables for the next iteration. We repeat until there's no more new branches found and exit the loop and regard the last generated input as the golden seed. After golden seed is generated, we can use it to bootstrap our fuzzer, which initializes multiple QEMU KVM instances to fuzz the driver in parallel. And when new input with new coverage is detected, it can pass it to our concolic server to achieve concolic fuzzing. We implemented Drifuzz using Panda Dynamic Analysis platform. It already supports dynamic tint analysis, and we augmented it to support concolic execution. And our fuzzing component is extended from previous KVM-based fuzzer KAFL. So we performed an ablation study to show how different components contribute to our coverage. With golden seed and concolic fuzzing, we are able to have 150% coverage increase than fuzzing with just random seeds. 5 of the 7 targets also have large coverage increase and statistical significance in 10 trial experiments. For the other 2, we see they are so simple that conventional approach is already good enough. In our evaluation with SymDrive, the previous symbolic execution work, we found path explosion is present, although other targets complete more quickly. For SymDrive, network interface failed to initialize in 3 out of the 4 drivers, while Drifuzz can initialize all of them. In the same time, Drifuzz is able to find 2 bugs where one was unfixed at the moment. We also compare Drifuzz with Agamotto, the state-of-the-art snapshot-based device driver fuzzer. Drifuzz is able to outperform Agamotto in both PCI and USB drivers with statistical significance in 10 trial experiments. We have 150 branch coverage increase in PCI drivers and 90% block coverage increase in USB drivers. In total, Drifuzz is able to find 12 bugs in 14 tested drivers. 10 of the bugs were found during seed generation. We submitted patches for all of them, and 11 are already fixed upstream. For the vulnerability we found, 2 of them were considered seriously enough for us to request CVE identifier. One is an out-of-bound read followed by an out-of-bound write with attacker control length in a PCI driver. The other is a kernel panic in a USB driver. So in conclusion, we found testing device drivers still difficult because we lack of the perfect seeds from real hardware. And we experience slow execution speed due to whole system virtual machine emulation. And we are currently working on this. We see that device drivers can have severe vulnerabilities that can possibly cause remote code execution and denial of service. From evaluation, we show golden seeds can make testing much more efficient and effective, and it can be reused for further driver fuzzers. You can check out our source code on GitHub. We are also artifact evaluated as available and functional. And that's it. I'm open for questions.